All right, everybody, welcome to Earth Science. If you were here the day that we did this sheet, then you don't need to be watching this video. You can just use those ideas, jump right to the classwork that's part of this assignment, and you're good to go. If you were not here, let's talk really quick. The purpose of doing this sheet is just to pop through some of the labs we've been doing and just kind of put us all back on one page. People have been working in labs at different paces, different angles of it, so it's valuable once in a while to just step back and say, hey, what are we doing here? What are we looking at? So specifically, these three vocab words that we got to have down pretty well are the three forms of energy transfer. Doesn't it? Transfer. The ways that energy can move about this solar system: conduction, radiation, convection. So if we were doing like full sciencey definitions, which you know I rarely do, we would say conduction is energy transfer by blah 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 blah, right? Let's keep it short and simple and just kind of like the basics on what these things mean. Conduction, this is the one by essentially touching. You need physical contact for conduction to be a thing. It's energy transfer by molecule to molecule contacts. You will do a lab soon, or if you're doing this assignment later because you missed it, you've already done this lab, where energy conducts along this aluminum bar by molecule to molecule contact. If you've ever heard the idea that when something's hot, the molecules within it, they're all shaken, right? And if they get hotter, they kind of shake faster, and then they bump into other ones harder, and then that will like transfer that energy through this metal bar by physical contact. That would be conduction. We will do that lab by putting one of these in a hot cup of water, one of these in a cold cup of water, sealing them off, and seeing the energy go from one to the other. Radiation is kind of like the lamp lab that we did. This is transfer through like electromagnetic waves. So let's just say waves through space. Probably should say electromagnetic. And that fancy scary word refers to all of the forms of energy, some being like, just visible light, things you've heard of like ultraviolet, infrared, radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. They can get dangerous to your cells down on this end, but other ones no effect on you whatsoever, right? So when energy transfers through these waves, which can go through space, some of these can go through like solids, right? Radio waves are going right through you right now. Anytime it's a transfer through those waves, that's what we're looking at with radiation. And again, you did it with this lab right here. Energy radiated out of this light bulb and entered into those two cups. Yours looked a little different, but same principle. Okay. If you've been near a fire and like felt that glow, or if you have a wood stove, that cast iron, the whole thing gets hot and it like you feel like it radiating heats. Radiation. Convection, I don't really have a lab for this. It is the flow of a fluid. And fluid means liquid or gas. So inside the pot here, the radiation you'd feel as the wood, especially once it turns to, excuse me, once it turns to embers. Convection could be like the flow of the water inside of this as it boils. If you've made macaroni and cheese and dumped the little macaronis in and seen them whipping around, convection. And conduction could be holding onto the handle as the energy conducts down the handle. All right, got to have those down. Those will be a thing. Let's also jump over here to specific heat. This is where the sand versus water lab really has an important idea that's hiding in here. What is specific heat? This is a big idea. Specific heat is amount of energy needed. So it's how much energy does it take? All right. Look at the label here. We can kind of define this with what this label is. And it looks a little intimidating. Joules per grams times degrees Celsius. But let's break it down. Amount of energy needed. That's what joules are. Joules are a unit of energy. How much energy is needed to heat? Really, let's just keep it short. Heat a substance. That's it. Even though I made this big, huge box. Amount of energy needed to heat a substance. How many joules does it take to get 1 gram to change by 1 degree Celsius. If it's liquid water, it takes that many. If it's water vapor, it takes that many. If it's iron, it takes that many. That much energy is needed to get this something to warm up by a degree, 1 gram of it. Now, of course, you're usually heating more than 1 gram, and you're heating it by more than 1 degree C, but you just multiply it, right? What you want it to do, there's good news. You want it to actually run any numbers in any of this. But conceptually, there's a very, 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 very important idea, which is what does it mean to like have a high specific heat, or what on this chart would be really hard to heat, even if you don't know, can't like grasp what 4.18 joules like is. I can't either. I'm with you. We can at least say in a relative sense that's higher than all of these other ones by a pretty large margin, which means, and if you're only going to pay attention to one thing out of this video, this is it. I'll put an exclamation point for the people that are doing what you shouldn't do, which is just watch without listening. Listen, listen, listen. What does that mean? 4.18 means that water heats and cools slowly. It takes a lot of energy to get water to heat up. That might feel weird because you heat water all the time. You do it in, to make coffee, tea, pasta, whatever, right? Excuse me. But it does take a lot of energy to get it to warm up, which has a lot of effects on how we use it. Depending on how you heat your house, a lot of people, I have wood stove as my main, but as a backup, we've got a hot water boiler in the basement. And this is reasonably common, or Inflow radiant heat is a newer example of this, but it uses water. So if you have those long like things along the base of your walls, sometimes those are electric, they're just plugged in. A lot of them are just a hot water pipe. So we have a boiler that heats water, and it takes a lot of energy to do that. It's expensive to heat water. The advantage is that once you heat it, it cools slowly. So then you can send it in pipes all throughout your house. It circulates, and as it goes through those pipes, it radiates its heat out into the room. If you'd say, well, why don't we use something that is less expensive to heat that heats easier? These are all solids, so it'd be hard to imagine. But what if there was a liquid that does? They make them. There are. Well, if they heat very easily and quickly, they're also going to cool very easily and quickly. So they would give their heat back out like before the pipes even left your basements. So water is kind of an ideal material to use for those things. Plus, we all have water running into our houses anyway, so easy peasy, right? Now, this is going to have a big effect on climates. This is where if you get into labs with lessons D and E, you're going to have to really think about this land versus water thing. And if water heats and cools very slowly, what does that mean? I'm not going to, we'll skip that part over there. We don't need to write anything over there. Let's over here draw. We've done this before. I know that it's kind of tricky. I'm going to draw a wavelength of energy that would be coming from the sun. And I'm going to have this hit land. Go through the atmosphere. That's what this, that's what this line is. Like that's the atmosphere, right? Not to scale. Here's the Earth, and this is my attempt at a drawing of North America spinning eastward towards us. Simultaneously, I'm going to draw another one that hits the ocean. Just like this lab that you did, there's a giant difference in how these two heat. If you put an equal amount of energy on both, which was the point of this lab, we put an equal amount of energy on both by having them be the same distance from the light bulb, which one heated more? And if your experiment worked, which most did, the sand one heated up a lot more than the water one. The water one heated up very slowly, but it also cools off very slowly. That's the lesson with that. Now, that's going to have a huge effect, and this is the purpose of the lesson D, temperature ranges. What if you lived in a city like right about here on my weird map of the United States, right about New York City-ish or Rhode Island-ish, and compare that to a city that was like way inland at the same latitude? What's the effect? If you live here, water, and I would like to add this, even though you already wrote it, let's do it again. Water heats and cools slowly. If you live right next to the water on a coastal city, when the sun hits you in the summer, it's also got to heat that water. And your area, your region will not get as hot because of that. Go inland. If there's no major ocean there, the sun's just beating on the land. Like you demonstrated in this lab, land heats very easily, so the temperatures are going to go way up. Flip over to winter. Water cools very slowly. Land cools very quickly. So if you're over here, as that ocean very slowly cools off, it actually keeps you a little bit warmer. You're not going to get as cold in winter. Up here, just drops right off. So I lived in Minneapolis, Minnesota, which is one of the cities, I believe. Well, maybe not. Could be one of the cities in the lab. But we got really cold in winter, which I kind of knew when I was going in there. And I'm talking, we would have wind chill days of like -30, -40. There were no snow days or hour delays or anything like that. We went to school. Um, and I knew it was going to be cold there, right? Everybody kind of knows that. What I didn't necessarily expect was that then in the summer it got to be really, really, really hot there because you're not near an ocean to moderate that climate. Oceans scrunch that range down. Remember that idea of range we did with tides? Not as hot, not as cold. Go inland, you get hotter and you get colder, a larger range. We get that to a smaller effect here on Lake Ontario. Lake Ontario, there's a lot of water in there. It doesn't freeze over. There's enough water that from the sunlight hitting it all summer and it absorbing energy, like 800 feet deep at its deepest point, really a lot of water. It holds on to enough heat energy that it doesn't freeze over. Now, the land, in the last like week, the air in the land has gone down below freezing, like that. Water, though, with its higher specific heat, holds onto that heat a lot more efficiently. It stays a little bit warmer. So if you live like right near the lake, that lake like is like a heat battery. It will radiate its heat back out to your house all throughout the winter and keep you a little bit warmer. Even though it's like a great lake in winter, it feels awfully cold. You're actually a little warmer because that lake is radiating heat. It's not frozen. It's warmer than the air. Go away from the lake, even as far as like neighboring towns like Lowville or down towards Syracuse, they can get colder because that lake isn't radiating heat all winter long. And then flop it in summer, you'll be a little bit cooler because that lake takes so much energy to get it to warm up. All right, good stuff. Let's just really briefly remember how the greenhouse effect works. It is not just energy coming in and getting trapped, it's energy coming in and heating up Earth's surface. And when things are warm, and if I can ever find a charger for this, I'll show you that when things are warm, they give off infrared energy, which is a longer wavelength, and that is what gets trapped by Earth's atmosphere. So let's chuck that in there, infrared. All right, sound good, everybody? Thanks for tuning in. Move on to the classwork. Good luck.